So the title of my presentation is Proportional Topology Optimization with Maximum Entropy-Based Mesh Test Method for Minimum Compliance and Stress Constraint Problems. I'm Dr. ZUllah from the Advanced Composite Research Group in the School of Mechanical and Aerospace Engineering at Queen's University, Belfast in the UK. My co-authors are Dr. Basirullah, Dr. Wajid Khan, and Professor Sirajul Islam from the University of Engineering and Technology, Peshawar, Pakistan. So proportional topology optimization is presented here with maximum entropy based mesh test method for 2D problems, linear elastics, for both minimum compliance, which is we referring here is PTOC, and stress constraint problem, which is we referring here is to PTOS. So PTO is simple, non-gradient, accurate, and efficient method as compared to the standard topology optimization method, and therefore it is straightforward to implement in computer program. Constraint is imposed on the global structure, and therefore these are considered as heuristic method. The maxent or the maximum entropy basis functions possesses a weak canonical data property and are more efficient as compared to the standard MLS basis functions. And due to this weak canonical data property, it allowed to impose the essential boundary condition the way we do in FEM. And the Young modulus for each background cell is calculated using the modified SIM method. And we are using the open source preprocessor qubit to construct and discretize the complex geometries. Now, the element-free Galericon method was proposed by Bilichko in 1994, and he used MLS basis function, which do not possess weak canonical data property, and therefore the essential boundary condition were implemented using Lagrange multipliers. In the maximum entropy based meshless methods, which was proposed by Sukumar and Arroyo. So these shape function or basis function possesses a weak canonical data property on the boundary, and therefore we can impose the boundary condition the way we do in FEM. So the discretized system of equation is similar to the finite element analysis in the maximum entropy mesh test method. So K here is the global stiffness matrix, and then the F is the force vector, which we can calculate from the traction and the body load here. The maximum entropy shape function or basis function are calculated using this equation here, where Zi is calculated using this equation, where W is the weight function, lambda 1 and lambda 2 are Lagrange multipliers, and Xi and Yi are the shifted coordinates. Z is calculated from this equation here. So Lagrange multipliers are calculated by minimizing this function here, where this F is just log of this Z. Now the stress constraint topology optimization. So first we will start with the stress constraint. So we call this PTOS. So PTOS search for the optimal design by minimizing the available material or volume fraction for constraining the stress to user defined limit. So this is the main equation here, that we have to minimize the volume, and these are the constraints. So the equilibrium condition, the condition on the stress, and then the density is between 0 and 1. And we are using here the modified SIM method to calculate the Young modulus for each background cell, and then we calculate the stress at the center of each background cell, and then from the stress tensor we calculate the von Mises stress, which is by using this equation here. And the convergence criteria for the PTOS is just the maximum von Mises stress minus sigma l is equal to eta, and eta is a small number here. And if the maximum von Mises stress is greater than the user defined limit, then we add material, otherwise we remove material using this equation here. So Tm is the target material, Cm is the current material, and Mm is the move material here. And we calculate the move material using this equation here. So 0.001 into the NBC, which is the number of background cells. And then material is assigned proportionally to the one measure stress using this equation here. So Rm here is the remaining material, and sigma Vm is the one measure stress for each background cell. So if the one measure stress is high, we add more material, and then Rm here is the remaining material, which you can calculate from the target material minus the actual material. And Q here is the degree of proportionality, which is a parameter here, and we can change Q to vary this equation. Finally, we also use the density filter using this equation here. So W is the sort of weight function, which is we are using a cone type of weight function here. And finally, the density in the current optimization iteration for each background cell is linearly blended with the density of the same background cell in the previous optimization iteration using this equation here. So rho I previous is the density in the previous iteration, and rho I opt is the current density. So we are using this alpha. So alpha is what we call is the blending parameter here. So the algorithm for the PTOS is shown here. So first we set up the problem, calculate the domain of influence, calculate the or set up the density filter. Then we calculate and save the basis function at the start of the analysis, so to save computational time. And we also calculate and assemble external force vector, which is constant for each iteration. And then we in each optimization iteration, we calculate we calculate global stiffness matrix and calculate the stress and compliance. And then we check for the convergence criteria. If the convergence criteria are satisfied, then this is end of the analysis. Otherwise, we go to the internal loop here, where we add and remove material based on the one measure stress. So if the one measure stress is greater, we add material. Otherwise, we remove material. And then the target material or the remaining material become the target material. And then we check for the remaining material. If it is less than this small value, then we update the density using the density from the previous step, and we go to the next optimization iteration. If not, then we go to the internal loop here, and then we assign remaining material to each background cell proportional to its one measure stress. We apply the density filters and limit, and the limit is because to make sure that the density is between 0 and 1. And then we calculate the actual material, and then calculate the remaining material, which is Tm minus Am. And then this loop will continue until we satisfy this condition. For the PTOC, which is minimum compliance topology optimization, so it's search for the optimal design with minimum compliance and subjected to the volume constraint. So this is how we calculate the compliance. You can calculate this for each based on each background cell, or this you can calculate this for the global stiffness matrix and global displacement. And these are the constraints. So the equilibrium condition, the volume constraint or mass constraint, and then this is the density, which is between 0 and 1. But we are using a minimum value just to avoid numerical complications. And again, in the PTOC, which is this is how we assign material to each background cell based on the remaining material. So we are using the compliance here, and again Q is the same proportionality parameter. In the PTOC, we are using this criteria, so which is we are checking the density up to optimization iteration. So n is 1, and then n minus 1 is the previous one. And if it is very, very small, then we will stop the simulation. So the algorithm is given is here. So we start the similar to the previous case. We set up the problem. We set up the domain of influence, set up the density filter. We calculate the max and basis function and store it. We calculate the external force. We then we calculate the target material. In each optimization iteration, we calculate the Young modulus, calculate the stiffness matrix, calculate the stress and compliance, and then we check for the convergence criteria. If the convergence criteria satisfy, then we end the simulation. Otherwise, we go to the inner loop where we take the remaining material is target material. And then similar to the previous case, we check if the remaining material is small. If it is yes, then we update the density using density from the previous step and go to the next optimization iteration. Otherwise, we go to the internal loop and we then assign remaining material to each background cell, in this case proportional to its compliance, and then we apply density filter and limit to make sure that the density is between 0 and 1, and then we calculate the M material, which is the actual material, and then the remaining material is the target material minus actual material, and then we do this iteration until we get this RM, which is the remaining material is less than this value here. So now to show some examples. So the first example is the MBB beam. This is the boundary condition, loading and dimension of the problem. These are our input material parameters. So Young modulus is 1. Emin is a very small value here. Poisson's ratio is 0.3. Penalty parameter is 3 here, which is used in the SIM method. L here is 40. The R min, which is used in the density filter, is 1.2. Volume fraction is 0.35, and the influence domain multiplier is 1.5 here, which is used in the mesh test method. So first we are doing some parametric study on these two parameters, Q and alpha. So here we are using Q, which is from 0.25 to 3, and alpha is from 0 to 0.9. Again, for the parametric study, we are using a relatively coarse mesh or discretization, which is 20 into 60 background cells are 21 to 61 nodes. And then we are using 100 optimization iteration. So in this figure, you can see that in this table that we have Q on this side and alpha on this side here. The minimum value that you can see for the compliance is 299.13, and then the green are the values which is within 10% of this value. So this means that for these values you can get a reasonable optimization geometry here. So in this figure here, we are plotting all the values from 0.4 to 0.9 with the alpha, and then the parameter Q is from 0 to 3. And again, we can see that these are the optimized geometries at the end of simulation for example, for alpha is equal to 0.5. And then we can also see the optimized geometry for the end of simulation for these different alphas here. So for alpha is equal to 0.5 and Q is equal to 0.5, 0.75, 1.25, and 1.5, which is these values here. It gives expected optimized geometries, which is you can see here. But for when the Q is greater than 1.5, which are these geometries here, so it gives unreasonable geometries with very high compliance values. Similarly, for alpha is equal to 0.7, 0.8, and 0.9, which is these three, it provides reasonable optimized geometry. But for alpha is equal to 0.4, which is this one, and 0.5 is this one, and 0.6 is this one, it provides unreasonable optimized geometry with very high value of the compliance. Similarly, for the PTOS, again, here we are using the same Q and alpha and the same discretization. And again, as you can see, the minimum value here is 249.14, which is this value here. So for these values, which is the green one, is within 10% of this minimum value. And again, we are plotting this from 0 to 0.4 for alpha, 0.3. And then we are plotting it compliance with respect to parameter Q. And again, you can see that for alpha is equal to 0, these are the different geometries. And then we are also showing the end geometries for 0.3 and 0.2, which you can see here. So as you can see, with a few exception, all these are reasonable optimized geometries. Now again, in this case, we are doing some convergence studies. So if we increase the number of background cells, as you can see here, and for the PTOC, we are using alpha is equal to 0.5 and Q is equal to 1. So these are the optimized geometry. For the very fine discretization, we are getting some more additional details here. And again, these are the compliance versus iteration and maximum one measure stress versus iteration plot. And these are the, again, also given in the table here, the maximum number of iteration, the one measure stress, and the compliance for all these values. And as you can see, the compliance is decreasing and maximum one measure stress is increasing with increasing refinement level, as you can expect here. And now for the PTOS case, we are using the same refinement levels, but here we are using alpha is equal to 0 and Q is equal to 2. And sigma L, here we are using from the previous PTOC cases. These are the optimized geometries here. And these are the compliance versus iteration and the maximum one measure stress versus iteration plot. And here we are comparing the comparing the PTOC with the PTOS. So as you can see, for the PTOC, for the PTOS, we are getting almost similar compliance, are in most cases a small value of the compliance and less number of iterations. Now for the second example, which is the L-shaped bracket. So here we are using these are the input parameter, which is similar to the previous case. And here we are using these number of background cells and nodes. And again, for the PTOC, we are using alpha 0.5, Q equal to 1. And these are the compliance, and these are the maximum one measure stress plot, and these are the optimized geometries. So for the very fine discretization, we can see here some additional details. And these are the plot for the PTOS for alpha is equal to 0 and Q is equal to 2. So, and again, these are the optimized geometries. So again, for Q is equal to 2, we can see that the optimized algorithm is trying to avoid this sharp corner here. But if we use Q is equal to 1, then we will be getting the similar structure as the PTOC. And these are the comparison of the PTOC and PTOS with Q is equal to 2 and Q is equal to 1. For Q is equal to 1, we are getting the convergence very quickly as compared to the PTOC and PTOS with Q is equal to 2. Now, the final example here is just to show the that the algorithm work for complicated geometries. So we are considering these complex geometries. So serpentine beam, which you can see is here. The hook problem, which you can see is here, fixed here, and the load is applied here. And the range problem, which is fixed here and a load is applied here. And these are the discretization for these problems. So here we are getting the number of background cell is about 5,000, 5,000, and 4,000. So for the first example, this is the hook problem. This is the optimized geometries, and these are the compliance and maximum one measure stress plot. Here we are using PTOC, PTOS with Q is equal to 2, Q is equal to 1, and Q is equal to 0.5. Similarly, we are doing the same for the serpentine beam. For Q is equal to 2, we are getting some sort of like a fluctuation in the plots. And for Q is equal to 0.5, it's taking too long to converge. And similarly, you can see these intermediate densities there. The similar case we can get from the for the range problem. So finally, to summarize the presentation. So here we presented the PTO with maximum entropy based meshless method for two-dimensional linear elastic structure for both minimum compliance and stress constraint problems. The PTO is simple, non-gradient, accurate, and efficient method as compared to the standard topology optimization method, and therefore it is straightforward to implement in computer program. Constraints are imposed on the global structure and is considered as heuristic method. The maximum entropy basis function possesses weak canonical data property and are more efficient as compared to the standard MLS. The max and basis function and special derivatives are calculated only once at the startup simulation to improve the computational efficiency. And then at the end, we show a variety of numerical examples with both simple and complex geometries and structural and unstructured discretization to show that accuracy, efficiency, and robustness of the both PTOC and PTOS algorithms. So thank you very much for your attention.